Hey everybody, welcome to CS302, and I hope you all had a nice semester break, and now we're back, and this is our first assignment of the semester. And then for this assignment, we're going to implement cocktail shaker sort, and this is essentially just bubble sort, but a little bit more efficient, so it's a bi-directional bubble sort. And in this semester, we will spend more time talking about sorting, and you will sort of at some point we'll discuss like why this is a celebrated closed problem because, well, it's already been solved. A lot of work has been done with sorting, and we've really discovered the most efficient way to sort a list. Of course, that'll be discussed further in the semester, so I'll just sort of not discuss that right now, but rather talk about the assignment. So the first thing before we can even begin to talk about the implementation for cocktail shaker sort is we're going to talk about this two-directional linked list class. Okay, so here is the linked list header file. And in this linked list class, it'll be a templated, or this is a class template. So as you've done in CS202, you understood what container classes are in C++, where they can essentially store any data type. So a vector or list are the same thing. They can store a list of integers, doubles, any type you like. So we're going to have our custom linked list class also be able to store a list of different data types. So let's go ahead and just first discuss the very beginning parts of this. So here's our linked list class, our template, and then we're going to have this struct node. Now I could have made it into a class node and made all the members public, but if I do that, it's just really an overcomplicated struct, if you will. So remember, each element of the linked list will be a node. A node contains some data field, which will be of whatever type you wish. So T will be our placeholder. And then we have these two pointers for previous and next. So it's going to be a two-directional linked list. Now, let's discuss the iterator class. So I'll go over some examples here in the video, but the iterator class, as you can see, is actually implemented for you. So you don't have to worry about the iterator class. You can just simply use it. But I will go over how you actually would like to use this possibly in your program. So this iterator is really just a way to, I guess, have pointers, but at the same time, we mask the pointers inside of the class. So the iterator is going to serve as a pointer when we're going to be outside of the scope of our linked list class. Let's go ahead and go through the iterator class quickly, just a quick rundown, and then I'll show examples of how the iterator can be actually used. So for iterator class, we have this private field node star current. That tells us, so this iterator object, it tells this iterator object which node it's going to be pointing to in a linked list. So that's going to be the only private member in the iterator class. Now, the iterator is a friend class to linked list, so the purpose of that is so if you were to actually declare some iterator object in the linked list class scope, you would be able to access the iterator's private members. Now, you're not going to have to use an iterator class in linked list. You can just simply use a node if you want, but if you were to use iterators in a linked list class, you can access private members directly. That's what the friend class right there means. So here's our two constructors. So our default constructor sets the iterator's current to null pointer, making this iterator a nil iterator, if you will. The second constructor will just simply pass in some address, and it's going to assign that iterator's current to point to whatever x points to. So pretty simple. Now this operator star, that's going to work as the dereference operator for this iterator class. So whatever node the iterator points to, remember, current is going to be the address stored in the iterator. So whatever node this iterator points to, it retrieves that node's data field, which you can see right there. And of course, I will show an example as to how this works. Then we have our, I think I jumped a little too far. There we go. Now we have our plus plus and minus minus operators. So this iterator operator plus plus int, this is going to be a postfix operator, which means the plus plus goes after the iterator object. And then this plus plus right here doesn't have the int, which means it would be a prefix operator. So it would be plus plus, it goes before the iterator variable. So think of this like in CS135, when you had an integer variable, if you had, let's say, integer x, x plus plus, remember, it increments x by 1 first, and then it retrieves the updated version of x. If you have plus plus and then x, it returns x's original value, and then it increments it by 1. And again, it's not going to be very important. Actually, you can treat these both interchangeably, but if in case you want to have a prefix and postfix, but really the plus plus operator, prefix or postfix, is going to essentially move iterator one node over to the right. And again, this operator is written for you. The minus minus, same idea. We have a postfix and prefix version, and the minus minus operator is going to move the iterator one node to the left. And again, it's written for you, so you can just, just call these functions in your main program, because you're going to have to use this to be able to iterate and move through the linked list freely as if you did have a pointer in main. Then we have our comparison operators going to compare between two iterators if they point to the same node, or if they don't point to the same node for equals, not equals. So that's our quick rundown of iterator class. So now I'm going to quickly discuss the linked list content, and then I can just show some examples so you can help you visualize how this linked list class and iterator class, how they work together to allow you to implement or be able to maintain this linked list. Okay, so now here's the rest of the linked list content. So for our private members, we have a node star head and node star tail. So it's going to be a two-directional linked list with a head and tail pointer. So these two, node star head points to the first node, the leftmost node, the head node, if you will, and node star tail points to the end node. So I do have all documentation for the member functions right here in the PDF, but I'll just discuss it right here in the video. So our constructor right here just simply sets head and tail both to be null. So it's going to initialize an empty linked list. Now, this constructor is going to be our deep copy constructor. So you have to do a deep copy of your linked list over here. So again, a little recap from CS302. Then we have our deep copy assignment operator, which is going to just do a deep copy of the assignment operator, fairly similar to the one from CS202. Then we have our destructor, which will deallocate the entire linked list. Now, these two functions, push back and push front. Push front and push back. So push front is going to be a head insert, and push back will be a tail insert. And of course, you can use pushback function actually in your copy constructor and assignment operator, because you're going to have to kind of one by one deep copy each node individually when you want to do a deep copy of a linked list. So very elementary, but again, a little recap from CS202. And the begin and end functions, I don't have these written for you in the PDF or in the sample or in the skeleton code, but the begin function is very simple. This function has to return an iterator whose current equals head. So in this function body, you can simply just create a local iterator variable, assign its current equal to head, and then return that that local iterator variable. And the same thing for end, except this one end function returns an iterator whose current contains tail. So again, you can define an iterator variable, a local iterator variable in the function, set its current equal to tail, and then return the iterator. So this is, for the most part, relatively simple. You may have to look over your notes from CS202 for push front, push back, and possibly for your copy constructors, but the copy constructor and assignment operator is stuff that you probably covered in CS202, so just sort of recap those notes. Now here's the real challenge you're going to have to do. It's going to be the swap nodes function. So for swap nodes, you don't want to just simply swap two nodes data fields. You want to physically swap two nodes in the linked list. So I'm going to right now just give you an idea of how you want to do that. And after we have that swap nodes done, we can then proceed and talk about the actual main program you're going to have to implement, the cocktail shaker sort. Let's first go ahead and spend some time visualizing iterators, how to traverse linked list, and then of course the swap node function. Okay, so let's consider this linked list right here. So suppose we define, let's say we're in our int main scope right now, and we defined our variable list. And suppose we did a bunch of push back and push fronts to create this linked list right there. So again, we create a linked list of type char. So every node in this linked list, its data field will contain some character, which I have defined right there. Now, I'm not going to go over how to push back and push front work because those are relatively reviewed from CS302. So I would just suggest look over your notes on that and just try to re-immerse yourself with that. It's not so complicated to do all those, so relatively, I guess it's more of a review from CS302. Now, we also define these two iterators, I and j. And it's actually very bizarre, the declaration for them, because we have this ll char followed by a scope operator followed by iterator. You're probably wondering, why is that? Well, it's because iterator is defined within the linked list class, if you can see here in a PDF. So in order to be able to access the data type iterator, we have to first enter the linked list class scope, and then we can actually access the iterator type. So for that reason, we have to use a linked list followed by char followed by a scope operator to enter a linked list scope, and then we can access this public class definition for iterator. So now we have I and j defined like this. And for both cases, we use a default constructor to initialize both I and j. So I and j's current fields will both contain null pointer at the moment because that's what the default constructor does. So the iterator is actually used to traverse the linked list. So it's a way to give us the flexibility to traverse it as if it were pointers, but I and j themselves are not pointers. They contain pointers inside of the objects, but they themselves are not pointers. Now, what you can do in your programs, you can do something like I equals list dot begin. Now list.begin, it returns an iterator whose current is pointing to the head node. And we're going to assign that iterator to I. So the result is going to be that I's current will point to that node right there. And then likewise, I also could do something like this. J equals list.end. Remember, the end function returns an iterator whose current points to the tail, and then we're going to assign that iterator to j. So in other words, j's current, it will contain the address of our tail node. So we can set our iterator to the begin or to the end. We can't set it anywhere else because remember, linked lists can only be traversed sequentially, but we can start from the head or from the tail. Then of course, if I were to do something like this, I plus plus, or I could do plus plus I, either way it will work, is going to update. So I's current now is going to point to the node afterwards. That I could then just do j minus minus, and then I can set j to now point to the node to the left of where it used to point. So really, all those do, it just allows us to move. Plus plus moves to the right by 1, and minus minus moves to the left by 1. Of course, I could do I plus plus again, and j minus minus, I can do j plus plus, and so forth. So really, just allows you to very flexibly traverse linked lists, just like with using a pointer. So really, I mean, not too tricky. And of course, if I were to do something like, cout star I, remember what the star operator function does. It's going to just return, if you look at the PDF here on the left side, it just simply returns, where is it? There it is. It returns the current data field. So in other words, I points to W, and W is the data field of the node that I's current points to. Other words, it's going to return W and outputs W right there. If I do a star J, it returns Y. So again, those are just ways to just simply retrieve data in each node and traverse each node using this iterator, which really behaves like a pointer, but it sort of hides all that pointer content. So in main, we don't really see the pointer, but internally, the pointer is inside of the iterator objects. So then again, you also can notice that the head pointer is previous contains null, and tails next contains null as well. So make sure you have those also set. Otherwise, you won't really be able to tell in main if you hit the end of the linked list. Now, of course, you can compare I and j to begin or end, but you're going to want to have these null pointers to make it a little easier so then you know when you hit the end of your linked list. So that's a quick rundown for how iterators work. And I also do provide some test cases. So in CodeGrid, I'm going to test out all of the members of your linked list class. So you can look at that code as well as a little bit of a reference for how iterators work. But really, that's about all there is for iterators. So now the next really big complicated portion is going to be the swap nodes function. Let's go ahead and discuss that next. So suppose we have our list right there, and we're able to write some code to position I and j into these two. So i's current refers to that node w, so I points at node w, and j's current refers to that node x. And then we want to go ahead and call the function, we want to go ahead and call the list objects swap nodes function and pass in I and j. So this is the only function in your linked list class where you're going to absolutely have these iterators because I and j are iterators that are being passed in. So this tells the list objects which two nodes you want to swap. Now, you can assume that I and j will always be adjacent nodes, like in this case here, because w and x point to each other. And you can always assume that I will be the left and then j will be the right. Now, of course, in your program, your main program, you'll have to do that. But to make things easier, I would just suggest in your main program, we implement this sorting algorithm. Just always make sure that you always pass it in where the first iterator is that left adjacent node, and the second iterator is that right adjacent node. Okay, so now that we know which two nodes we're trying to swap, let's go ahead and think about this code. Now, it'd be so much easier if we could just, do this. Just grab the data field from this node, put that there, and call it a day. That'd be great, actually. But there's a few things wrong with that. Not really wrong with that, but there's a few issues. One, it's too easy. And, we can't have things be too easy, actually, in CS302. And the second reason is because there could be an overhead with this. So, right now, in this situation, each node contains characters, so it's not a big overhead. But what if, let's say, each node contained large amounts of data? Then really, swapping data fields does have an overhead, actually. So we want to avoid that overhead. And in fact, a better idea would be not to swap data fields, but to physically pick up this entire, I'm trying to circle this entire node right here. There we go. I want to pick up this entire node. I'll put it here for a second. And pick up that node right there, drop it right here, and pick up this node and drop it right there. That's what we're trying to actually accomplish. That's our goal. So we're not going to swap data fields. We're going to pick up these two nodes and then just sort of physically, or I guess we're going to physically swap them in the linked list. So then the question is, how do we actually implement that? Let's go ahead and I'm going to reset this back to where it was. I think we're good. And now I'm going to just sort of pause the video and go back. So if I make a mistake, I don't have to keep on trying to cut the video over and over again. So let's go ahead. Now I'm going to just do a kind of a quick pause, and then let's go ahead and go over the details for how you want to implement this swap nodes function. Okay, this is my first attempt at this. Let's see how this goes. So anyway, right here, to be able to really physically swap these two nodes, we're going to have to really reassign these pointers to really, I guess, emulate this sort of moving these two nodes. So let's look at this for a second. So, for example, we want to possibly maybe create a few additional iterators or pointers, because I would recommend you may want to have maybe a pointer that points to the node to the left of I, and you may want to have a pointer also points to the right of J. And here's going to be the formula for this. So the node W, its left neighbor is V. So guess what? You're going to have to set V's next. So this node's next has to point to X. And X's previous has to point back to V. So now you can see that the node that comes after V is X. X points back to V. And now the same thing for Y. So Y and X kind of share, they're next to each other in this linked list. So now if you want W to be next to it, you're going to have to adjust where W's next has to point to Y, and then Y's previous has to point to W. And we're still not done quite yet, but we're almost there. And then what we have to do is you have to set X's next to point to W, and then W's previous has to point to X. And easy as that, now these two nodes are actually swapped in the linked list. So if you could try to imagine, like, these are a bunch of strings we have, and if you did all this rewiring, if you were to sort of take the head and tail and sort of pull or tug on those two nodes, what would happen is X would sort of go before W, if you will. So the end result is going to be like this. So I'm going to erase all of this content, but again, you can, of course, could pause the video and you can sort of look at that, but the end result is going to be this. Even drawing this up is, even redoing all this is going to take a while. Okay. And it's not going to be fully cleaned up picture, but here's what the result is going to be. This is like, does not want to cooperate with me right now, my pen. Okay, so here's the result that's going to happen. Okay, this is really, maybe try to use my mouse if I can do this. Okay, I think it's working now. There we go. Move this over here. So if you notice, what's going to happen is J also is going to move with its node, and so will I. So the result will be like this. I and J are going to also move with those two nodes. And the end result looks, like, I'm not sure I clean this up, but this is how it's going to be at the end. So modifying all those pointers are going to be the way we're going to emulate this. And now after we're done, everything is swapped, but the problem is I still want, so let's say right here, I was actually pointing to the second node of the linked list. Well, now the problem is I now points to the third node. So it's not very consistent. So you have to essentially afterwards, you have to swap I and J's current addresses. You want to assign J's current to where I's current is and I's current to J's. So 3 lines of code. You have to just simply swap the addresses only. Because the end result is you want to have it where I points to this node and J points this node. So now I still points to that second node in the linked list, and J still points to the third node, the new third node of the linked list. So you want to, at the end, swap I's and J's currents to make sure that they still point to the same position of the linked list after the swap. So really, you have to do a bunch of next and previous's. You have to simply reassign all these to emulate that swap. So I would suggest, as you write the code, draw it out line by line on paper. Each pointer reassignment is one C++ statement. After you do that, take your code and just simply trace that code out on the same piece of paper and see if it's consistent in both cases. If it's done, it will work. Now, this does not consider edge cases. For one, what if you have it where I happens to point to the head node and J points to the node after the head? Then what's going to happen is this head pointer is going to move with v, so the head pointer is not going to point to the head node anymore. It'll point to the second node. So you have to reassign the head pointer to, you have to reassign it back to the new head position. And same idea, what if I points here and j points there? Same thing, if you swap those two nodes, z will move in front of y, but the address of a tail points to also moves with z. So you want to make sure you reassign tail back to the new end node after you're done. So that's essentially a quick rundown of how you want to visualize swap nodes. So now we can finally get to the actual code or pseudocode for cocktail shaker sort. Then I'll go over a few of the input output and just simply how to compile the program and run it and so forth. Let's go ahead and now discuss the cocktail shaker sorting algorithm. So anyway, before I go into the main contents and the algorithm for the cocktail shaker sort, let's first discuss the input output. Input, pretty standard. You're just going to be given a set of integers. It'll be one integer per line. So you can just use the input extraction operator to parse the input. And you'll be given a file, but you're going to read in your content through Linux redirection. And again, I will go over that in a video later on. And I'll just sort of show an example run so you can see how that works. But very simple. There's no need for file streams because really you're just going to read it from the file. And really in CS302, we're not going to focus too much on input file name correctness because that's more of 135. So we're going to just use redirection to read the input. Very simple. You're going to have to create a linked list of integers. Now, again, you got to make sure your linked list is a template because some of the testing files I'm going to use to test out parts of your program, I'm going to have a linked list of strings. So you want to make sure your linked list works for any type, but really it's the template aspect. I don't think it's too complicated. But anyway, you'll have to read in each number one by one and then push back each number one at a time to a linked list object to build your linked list. So suppose in your file you have, let's say, 5 followed by new line 6, new line 10, and so forth. You just simply read each number one by one. So you read into 5, push back 5, then push back 6, push back 10, 8, 1, 2, and 4. And imagine you have this linked list. I don't have all the linked list details. This is more of a higher level view example, but imagine this is a linked list you had right there. And the output, well, you're going to have to simply just output the sorted list at the very end. It means you have some kind of a white space between each number. On code grade, I don't actually have it really look at white space, but make sure you have some type of white space to delimiter to make sure so you separate each number of the outputs. You can output each number at the end followed by a space or a new line, but some type of a white space delimiter is all you have to really worry about. So anyway, let's look at this cocktail shaker sort. So really, this is going to be just essentially a bubble sort, but a two-directional bubble sort. Somehow bubble sort works. What happens is you always have adjacent indices. Now, since we're using a linked list, not using an array, we're going to have two iterators. So suppose we have, I'll just use blue and red, like this. In your first pass, you're going to actually go from left to right. You're going to have to bubble the biggest element to the very end. So all you're going to be doing initially, you're going to have you're going to first start from the leftmost position of your linked list. So at the very beginning, you're going to start from the very start, literal start of your linked list. And from the very beginning, you have these two adjacent iterators. You're going to have to compare their values. So suppose we have, this will be I iterator and J iterator. So you can use star I and star J to retrieve the values 5 and 6 respectively and then compare. So since the value J is in fact larger, there's no swapping needs to be done because you want to have always the bigger element on the right among the two elements. And then what you do is you just move I and J both over to the right by 1. And then same concept. You then compare. So star I will be 6, star J is 10. So since the right adjacent node is bigger, then you don't have to do any swapping. And then afterwards, same idea. We move like this. And now we can see here that, okay, now the situation is star I is 10, star j is 8, so the element to the left is actually bigger. You have to swap nodes. So again, you would call swap nodes pass in I and j, and the result is, remember, it's going to just simply swap these two nodes. Now, of course, it won't only swap data values, but end of the day, this will be the result. And after that, again, we move it over to the right by 1. Now in this situation, once again, the element to the right is not in fact larger. We have to swap the 10 to 1. So 1 goes here and 10 goes over there. Again, we just keep moving until we can't go any further. Same idea over here. Since star I is larger than star j, we swap these two. Then we move over here. And again, same idea. Since star I is actually larger, we swap these two. So now the result is the biggest element has now bubbled all the way to the end of your list. So now, I'm going to put this green line here. So everything to the right of that green line is now sorted. So what you're going to do now is you do the same exact procedure, but now you did your first pass from left to right. So now you're going to have to go from right to left. So what I would do now is I would reset my iterators. And now we're going to have to move from right to left. And then what's going to happen here is we do star I and star j. And in this case, since we're going from right to left, we want to make sure the left element is smaller. So since that element is smaller, you don't do a swap. So we move I and j over to the left. And right here, same idea. We don't have to do any swapping because the left element is in fact less. And then right here, we see that, oh, the left element is not less in this situation. We have to now swap these. So the 1 goes here, 8 goes there, and then we just move over like that. Same idea. We just have to compare. So since star I is not less than star j, we swap these two values. Then right here, again, since star I is not less than star j, we have to swap like so. And now we hit the end. We hit the very beginning of our list. So now we're done. So now everything to the left of that is smaller. So what happens is every time we do a pass, we have to essentially move these endpoints over. So the idea is, once again, when we do our next pass, what's going to happen, we start from here, and now we have to sort of bubble the biggest element over as far as possible. So if you were to emulate this, what's going to happen is 5 and 6, nothing happens. 6, 8, we're good. 8 and 2, we have to swap these two nodes. And then 8 and 4, we swap again. And then we're done. We're not going to go beyond this green threshold because everything beyond that is actually now sorted. So we have to move this threshold over to the left. So from now on, if you go beyond that green barrier, we stop immediately. And once these two barriers equal each other, we're done. Then the whole list has to be sorted. So these two barriers, in fact, are going to just be really possibly two iterators. So once I or j hit that barrier, then you know you are done with that, either the left to right pass or that right to left pass. So that's how we know when we stop. But there is an edge case to consider. Initially, you might have remembered that I didn't actually have any green barrier at all, because in our first pass in either direction, you wanted to go all the way until we hit null. But next time, we don't have to go all the way to the very, very end, because we can stop early, because once we, do a few passes, like over here, for example, once we're going to bubble 6, for actually in this case, I'm sorry, we'll bubble, let's say, from right to left now. Notice that what's going to happen here is we have 2 and 4 is fine, then 2 and 6, we have to swap 2 and 6, then swap 2 and 5, and now we hit that barrier, so we update it here. So now everything to the left of this barrier is less, everything to the right of this barrier is larger, which I actually do even say create two. So create a start of list, end of list iterators that denote the end and the beginning. So we can see here this green line, so this would be start of list iterator, this would be end of list iterator. And once the iterators equal each other, we're done. But there is an edge case to consider. The first one is on the very first pass, start of list, end of list are not going to be, well, you got to make sure you're consistent with that. So I don't want to give away too much right here, but the idea is there's an edge case, at least how I wrote my program. Since we don't have circular linked lists in this implementation, there will be an edge case to consider. And of course, after every pass, we always move the iterator to the one to the right or one to the left, depending on which pass we're in. And that's really it. So just bubble sort in two directions. That's the idea, really. So you essentially have to have I and j iterators and then move them one node to the right, one by one, using the plus plus operator when you're doing your left to right pass. On your right to left, you just have to move them minus minus. But you're always going to have these two iterators right here, so you can set I and j accordingly. At the very beginning, the very first pass, I will be set to the begin and j will be after I. And the first pass from right to left, you set j to the end, and then I is one less. But after that first pass, you'll always set I and j equal to one of these two iterators right there. So you don't have to start from the beginning, you start from this position or that position respectively. So again, I do give the pseudocode out there, and I did sort of give you a little bit of a high level trace. I don't want to go over every little detail, but that's sort of like the idea for how to implement this algorithm. Let's go ahead and now just go over how to compile this code, and I guess I'll show you the actual input files, and I'll show you the skeleton code I provide, so you can just take a look at that. So I can sort of also discuss that as well, and then of course the video would, at that point, I think I covered everything needed for the assignment. Let's go ahead and finish this up. Okay, so in the zip file that's provided for you on Canvas, this is a header file. So you can see here, you're not going to modify it, and you shouldn't, because on CodeGrade, you're not going to even submit the header file. There already is a header file there in the CodeGrade, which it will link itself to your implementation file. So really, you won't be able to modify. If you do modify the header file and modify your implementation file, then it won't actually link, and then CodeGrade will not even compile and you get a 0. So you probably shouldn't mess with this anyway. Now I do give you the implementation for Iterator right there, so you don't have to worry about that. Of course, our header guards there as always, so if in case we do redefine, we re-include by accident indirectly multiple instances of the linked list class, this will prevent any compilation errors, so header guards right there. And also I include l.cpp. This is actually a workaround where this will allow us to have a separate header file for implementation file, so I can test out all of your, because that way you have a separate header implementation, so it's easier to link your custom library to different mains to test out different parts of your program. So right here, actually I'll first start with this one. So this one also will be given to you already in CodeGrade, and I guess I heard, I actually saw on YouTube a few weeks ago how the new Gears of War game is coming out, so I'm definitely in that mode right now. So the names here are Gears of War themed. And you can see here, I do have a linked list of type strings. So again, if a templated class, your code should work for any type. So in your main for the cocktail shaker sort algorithm, you'll have linked lists of integers, but your class template should be able to handle any data type, including strings. So I just simply go over a couple of, this will be tested on CodeGrade. I give this to you. Now to compile this is rather simple. You have to only just compile a g++ ll insert.cpp, because we include the header file in this source code, and header file includes CPP files, so it just will compile everything together. If I run this, there's our contents. It should match this on CodeGrade. Now this is for, this is a linked list insert test. Sorry, there it is. Then deep copy test. I just simply test out to make sure your copy constructor and sovereign operator work correctly. So a very simple test of that. The swap test, I just do a couple of swaps and output the list accordingly. This just makes sure that your swapping is correctly working. So again, to test this out, you would just do g++ ll swap test.cpp. And for the deep copy test, it would just be ll deep copy test.cpp as well. So very simple to compile these programs and run them. So there's that. So now we're also going to be using on CodeGrade memory leak checker. That's also rather simple to do as well. Let's go over that deep copy test for a quick second. I could just compile it. So ll deep copy test.cpp. If I run this, that's the output your program should generate. It will compare this on CodeGrade. Now, to test it for memory leaks on Linux, remember it's just valgrind is the command. And then there's all p blocks are freed. So there's no issues at all right there. So anyway, we'll check it's on CodeGrade as well. So all you have to do is compile your program, valgrind on Linux, and then / your exe file. Now for the main portion, so right here in input01.txt, this would be one of the files you'd be given. And you're going to populate a linked list with all these numbers in this file. Now to read this in your program, once again, let's go ahead and compile our program first. So I have a g++ main.cpp, which includes ll.h, and ll.h includes ll.cpp, so it links it together. And if I do /a.out, all I have to do is use that arrow looking symbol, which is really going to, this is an input redirection. So we're going to redirect cin to now read from a different file. So normally cin by default reads from the command line, whatever you type over here in the command line. But if you do this, cin will be redirected to read from a file. So I'm going to give it input01.txt. So now it's going to read everything from this file using cin extraction operator, and it's going to now perform this sorting algorithm. We hit enter. The output should just be a sorted list. That's it. So that's going to be sort of the program you have to work on. So CodeGrade will do a bunch of these small tests. So I have several of these main files that are used to test out different parts of your linked list class. Then of course you have to write your own cocktail shaker sort in main.cpp. You will define your linked list object, populate it. Using iterators, you're going to implement that bidirectional bubble sort. At the end, output the results. And also on CodeGrade, it will also check everything for, it will check your comments automatically. I believe I have a threshold set 20% comments you have to have, which is not too high of a threshold, so it shouldn't be too stressful to comment everything. And of course, you have to have header comments as well, which is also included in the PDF. And also on CodeGrade, you'll be notified if you don't have header comments. So other than that, I think that pretty much summarizes the entire assignment. So hopefully this video did give you some assistance. So I guess happy coding and till next time.